Hello, everybody. I would say good morning, but if you are joining us from Europe, it's obviously evening time. So welcome to our webinar today. I'm pleased to have Diego on here joining us, Diego Marchetti from Rome in Italy, and he's going to talk about the flat dilatometer and seismic dilatometer for in situ testing. So Diego and I have actually known each other since we were kids. We both were the sort of brats growing up in geotechnical engineering world, where both our fathers were always going to conferences, and Diego and I would be, exploring the cities together. So it was fun to catch up with him. And now he's obviously taken over at Studio Marchetti from his father, and he's developed the seismic dilatometer. So it'll be interesting to hear a little bit more about that. It's really good software. That's obviously where Diego's strength is with his background in computer engineering as well. So he travels all around the world doing DMT and supervising DMT testing. So he is definitely the right person to give this presentation. So I think we won't, hesitate too long here. We'll go ahead and get started in just a few minutes. Just some other announcements for Calgeo folks. We do have a piezometer short course coming up on December 2nd. That's actually open to non-members as well. So if you guys are interested in learning a little bit more about piezometers, installation, data, that kind of thing, that is on December 2nd, and information is on our website at calgeo.org. And then we are doing a fun little holiday mixer. It's virtual on December 14th. We have a mentalist magician coming in, so that will be super fun. And that's on the evening of December 14th. So I think that's all of our announcements. To quickly go over this GoToWebinar software program, if you haven't used this before, I know it's slightly different than Zoom, but you do have a questions section where you can type in questions at any time during the presentation. I will see those come in, and we're actually going to hold the questions until the end of the webinar, and I will come back on and I will read out the questions to Diego. So hopefully I can understand all the questions all right, and we'll get those answered at the end of the presentation. So definitely type those in whenever you like, and if there's any questions that we don't get to, I will be creating a, hi Alessandra. I will be creating a report at the end and sharing that with Diego so he can contact you guys and get back to you. So we will go ahead and get started. Diego, do you want to come on the, let me see.
Hi.
Oh, there we are. Perfect. Alessandra, do you want to stay on video? You're on video right now. This is Diego's wife. She works also at Studio Marchetti. You can just turn off the little
Camera.
See if I can do it. Perfect. Okay. So Diego, I will pass this over to you. I'm going to go on mute, and then I'll come back on at the end if there's any questions.
Great. Great. Okay, so shall we start? I hope you can hear me.
Yes, everything sounds great. And then, oh, I do have that quick poll. So let me know, Diego, if you want me to launch the poll, just to see everybody's experience level.
Yes.
DMT? Okay.
You can do that during the presentation or before?
Yeah.
Or...
Okay, I just launched it right now. So if you guys don't see this blue quick poll window, just you might have to go from the full screen presentation, minimize it a little bit. There should be a little poll coming up. It looks like about half of you have voted, so it's going well. I'll give everyone a few more seconds. Just wanting to hear your experience level with the DMT. We're almost at about 75%. So it looks like about 14% never heard of it. We've got 42% some knowledge but no experience, 35% some experience or they've seen results, and oh, this just changed, about 10 or 11% are quite experienced. So I'm going to close that and just share the results, Diego, so you can see that. So it's mostly in the middle tier where people are somewhat experienced.
Great.
Okay,
Perfect.
we'll hide that.
Okay, let's start because it's getting late. So I will start my time now, 1 hour. So thank you, Kelly, for your kind presentation. Let me see if I can take this window out of the way. Is there any way to take the camera off here? Because it's larger than my presentation.
Yeah, if you press the little orange arrow, it'll minimize the GoToWebinar control panel, and
Yeah,
then
the
it'll
panel,
cover
yeah,
less.
but then I have a visualizer of, I see myself. Maybe I can
Oh,
close it. Yeah, I close it. Okay, great. Got it. Okay, so once again, thank you, Kelly, for the introduction and the presentation. Thank you all for participating to this seminar. We will talk about the flat dilatometer and seismic dilatometer for in situ testing. The aim of this presentation is to give an introduction on this testing equipment updated to the new features and the new developments we have done in the last years. There will not be time to go in the applications with the results, but what I want you to get from this seminar is to know what the instrument is, how it works, how you do the tests, and what results you can get from it. Okay, just as a historical note, the flat dilatometer was invented by Professor Silvano Marchetti, who passed away in 2016, and he invented the instrument in 1974. These are pictures of the last conference on the international conference, the third one on the flat dilatometer, which occurred in 2015 in Rome. And you can see several big people of the geotechnical world. Okay, in penetrable soils, direct push technology like SCPT and SDMT is taking over for everyday projects against the laboratory and CPT testing. Direct push technology is very simple, it's fast, it provides repeatable results and provides continuous soil profiles with depth. The results are available real time. In sands, recovering undisturbed samples is very difficult, so direct push technology is becoming the state of practice. In this presentation, we will talk about the DMT and SDMT. The SDMT is the combination of the flat dilatometer that you see in the top right with the seismic module mounted behind the blade for performing measurements of seismic waves, shear wave and compression waves. Now the blade, the DMT is a blade of stainless steel with a flexible steel membrane mounted on one of its sides. The test consists in advancing the blade in the soil by using some penetration rods and with a pneumatic electric cable running from the control unit at top into the rods and down to the blade at depth. The black arrow represents penetrometers or penetration machines that we will see in the next slides. A gas tank is required for generating the pressure, generally of nitrogen or compressed air, and a computer for the data acquisition, the automatic data acquisition. The test consists in advancing and stopping the blade every 20 centimeters, starting from ground level. And at the beginning, when the blade is advanced at depth, the pressure of the soil will flatten the membrane against its seating behind it. The operator will start to inflate gas, and when the pressure of the gas is in equilibrium with the pressure of the soil against the membrane will start to expand, and the A pressure is recorded. So A is the liftoff pressure. The operator continues to inflate the gas, the membrane will start to expand, and when it has expanded 1.1 millimeter, the second pressure reading B is obtained. The operator will then deflate after B, and when the membrane returns in the original A position, we have a third pressure reading called C, which is the closing pressure. Simple as that. 3 pressure readings every 20 centimeters, or most of the time only A and B, which are 2 pressure readings. To see this more in detail, we said we push or drive the blade at depth, the pressure of the soil, which are the red arrows, flatten the membrane, so the contact of the audio signal will be on. The operator will inflate, generating a pressure represented by the blue arrows. And when the pressure of the gas is in equilibrium with the red, the signal, the contact of the membrane will go off and the A reading is taken. Again, the operator continues to inflate, the membrane will expand, and when the center has expanded exactly 1.1 millimeter, a contact will go back on, and the second pressure reading B is obtained. After deflation, if the deflation is done with a specific valve, the closing pressure C is also recorded. Now, the DMT may also be performed with the automated dilatometer we have recently developed called the Medusa SDMT. It is composed of a battery pack, an electronic board, a hydraulic motorized syringe composed of an electric engine, a piston, and a cylinder, and a pressure transducer for recording the pressure, and a DMT blade of standard dimensions, so that the results are exactly the same of the standard DMT we have just seen, but the measurements are automatically performed by this instrument. I will not focus on the details of this new instrument, which was developed initially for offshore testing, because it is quite complex and expensive, but we are also using it on land. So to summarize, the DMT consists of taking A and B and eventually some C readings every 20 centimeters. Behind the blade, it is possible to add this seismic tube with two sensors, receivers, and an electronic board. At surface, the shear wave is generated with a shear beam hit by a hammer that hits horizontally against this shear beam, and the generated shear wave will travel in depth and arrive to the top and to the bottom sensor. The electronic acquisition board will amplify and digitize the data, send it up at surface in a matter of seconds, and this seismogram will be shown, showing that the wave will arrive first to the top sensor and then to the bottom, and the delay delta t is the delay in the arrival of the wave from the depth of the first to the second sensor. The shear wave velocity is then evaluated as S2 minus S1, which is the difference of the travel paths of the wave, divided by the delay, basically the definition of velocity. Differential space divided by differential time, for providing an average velocity in the half a meter between the two sensors. And from that, we obtain also the G naught or G max as the density of the soil times Vs squared. The software enables to acquire the seismograms by pressing this button with a configuration of parameters which the defaults are perfectly good at the beginning, and with some automatic tuning of the parameters, the operator does not have to be qualified to tune them. He is then asked to generate the shear wave, so a hammer hitting the shear beam, and in a matter of seconds, we see in the top image the recorded signals with the delay that we want to, that contains the information of the shear wave velocity. And below, the seismograms are rephased according to the delay that is calculated real time. So the system is able to evaluate the delay, and then it will plot the blue wave as it was in the recorded signals, and the red wave shifted backwards of the evaluated delay, so that the user may check that the superimposition of the phase of the wave more than the amplitude is correct, as is in this situation. Now, the shear wave velocity is given real time, and normally users are recommended to repeat 2 or 3 times the same measurement, and the variation coefficient is generally below 1%, but very good, up to 2-3%, acceptable to 5%, and this is how people normally do the test. If you get more than 5% or 10%, it means that probably there is some problem in the configuration of how you put the hammer or the tests. But all these details are given in the training, and this is the average quality of the seismograms you will obtain. Now, this system was developed and concluded in 2005, of course, improved with the years. And the first things that happened were comparisons, of course, with very high quality tests, in particular cross-hole tests. This is an example of the many comparisons you can find in literature in New Zealand between two cross-hole tests and the SDMT, showing very good agreement of the shear wave velocity. This is another published comparison in Brazil, where you can see a very good agreement between cross-hole tests and SDMT in 3 different test sites. Now, the main features of the SDMT are the following. First of all, the test execution is very rapid because it does not require to drill a borehole if the soil is penetrable. It does not require to wait time for the cementation of the hole as for cross-hole and downhole. You can take up to 2-3 hours to do a 30-meter test, concluding the DMT, or even less if you do just seismic measurements, and have the results available real time. The high accuracy in the evaluation of the delay is determined by the following points. First of all, the electronics is a customly designed acquisition system, which is able to amplify and digitize the signals at depth with a high immunity to disturbances and noise. And clear waves are really necessary to obtain a consistent and simple evaluation of the delay delta t and therefore of Vs. The second and maybe most important point is the true interval system with 2 receivers, which is in our opinion, more superior to pseudo-interval systems with only 1 receiver, where you would have to give a first hammer blow for the only sensor, for example, the top blue one, and then give another hammer blow after you went to a different depth, with a possible error in the depth. Even a small error can make a difference, with a different hammer blow, which can make a difference, with a trigger that can offset at a different time, whereas if you have 2 sensors recording the same wave, the trigger is the same, and even if it triggers differently, what you care of is only a differential measurement between their arrivals. So there is no chance that the pseudo interval can be as accurate as a true interval. And I would recommend you always to rely only on true interval systems. The VS evaluation is automatic. I would say 95% of our clients do not do any post-processing because with the training we provide for the test configuration, they are able just to give hammer blows and to obtain results of VS during test execution. And the results are operator independent and available real time. This is a LinkedIn discussion I went through some years ago, where there is a client who is asked to perform seismic CPT, and when he is asked to, he undertakes CPT first, and then he uses our SDMT to get the shear wave velocity, because he claims that there is less interpretation to do. For this reason, we were actually forced by clients to make a combination of the SDMT with the CPT, namely the SDMT cone or SDMT CPT. That means a CPT cone with the seismic without blade. And currently, we are in a partnership since several years with Calgeo, Geomill, and Pagani to provide these SDMT cones. Any other CPT system may be combined with the SDMT, provided there is, of course, cooperation with the constructors. Now, let's look at the penetration machines that can be used for advancing the DMT and SDMT equipment. Of course, the heavy truck penetrometer, 25 or even 30 tons, is the most efficient and productive way of performing these tests, because the blade can be advanced and pushed with that force without any lateral instability. A more economical solution may be to use a light penetrometer, like the ones you see in this picture, that are able to anchor and receive some reaction force from the ground, so that when they push, the machine does not go up. However, the DMT and can be used with many other possibilities, even with a dynamic, although not recommended in soft soils, with the SPT hammer, or pushed with a drill rig from the bottom of a borehole, or pushed alternatively to driven with the light penetrometer we have seen before, or driven by a drill rig, or any other way we can think of, as long as we can get the blade in the soil, possibly disturbing the less. So static will always be better than a dynamic, even though in very consistent soils, the difference between a static and a SPT can be, dynamic penetration can be very small, whereas in a soft soil, the difference can be very high, so it's not recommended. Let's look into detail how we could do with a drill rig from the bottom of a borehole. The torpedo system is this combination of a top adapter for allowing the cable, the pneumatic electric cable, to exit and connect to the drill rods, and then be taped to the drill rods in a borehole. And this torpedo is generally 3 to 5 meters long. It is lowered to the bottom of the borehole and then pushed every 20 centimeters. Generally, the first reading at 20 centimeters is a bit disturbed by the bottom of the borehole, but once you go up to 40 or 60 centimeters, disturbance is not relevant anymore, and the results are as if it was in a penetrable soil. This method, of course, is slower than a penetrometer because you have to alternate the drilling to the pushing, but it is able to overcome obstacles if there are that can be drilled, and then you can continue below, whereas with the penetrometer, you have to stop for refusal. Another possibility is to use the Shaka penetration method, again with the drill rig, by pushing penetration rods from the surface and advancing the instrument. Of course, the drill rig is not designed for pushing, but in soft soil, this has been used successfully. Of course, all these methods are possible also from a floating barge. In this case, it's a floating barge with a drill rig and with the Shaka method for 10, 12 meters below the lake floor. And in this case, we also did seismic tests with this seafloor hammer that you see in the picture. The Flat Dilatometer test, DMT, may be performed in any penetrable sands, silt, or clay. This means from very soft soils with undrained shear strength of the value of 2 to 4 kPa and moduli of about 0.5 MPa to very hard and stiff soils, almost soft rock, with very high values of SU and M. The blade itself is very robust and able to withstand push force up to 25 or even 30 tons. But generally, you have to beware of the rods, which can bend and arch and then break. The SDMT may be performed in the same penetrable sands, silts, and clays, but also in non-penetrable soils like gravel or very dense sand that may not be penetrated inside a backfilled borehole. More details are available in this publication and some updates that we may provide on the test procedure, which have improved this original publication. The max depth of the test we did were 135 meters in the town of L'Aquila in a pre-bored borehole, of course, filled with sand. Now let's look at the interpretation of the DMT results. We said that we come back from the field with A, B readings and eventually some C readings every 20 centimeters. Now, how do we get geotechnical parameters from these? So the first step is to correct the readings with the membrane calibration. Actually, it's not a calibration, but it's like a tear to account for the membrane rigidity. I don't want to go into this, but basically you will take A and B measurements out of the ground. So you will measure the rigidity of the steel membrane, and it will be subtracted to obtain the net A, B, and C values. The most important step is the second step, which is the evaluation of the intermediate parameters. So from the corrected readings, P0, P1, and P2, the intermediate parameters ID, KD, ED, and UD are evaluated, and each of them has a specific geotechnical meaning. We will see these in details in the next slides. The third step an important point. These are definitions, not correlations, which is really important because the correlation step occurs later from the intermediate parameters to the interpreted geotechnical parameters using correlations developed and published in 1980 that have proven to be still valid today for the major part of the soils. In particular, the constraint modulus M, the undrained shear strength SU, the earth pressure coefficient K0, over consolidation ratio, friction angle, unit weight, and soil description, pore water pressure in sands, and distinguishing between drained and undrained behavior of the soils. This is a chart of the summarized formula of Marchetti 1980 with the field readings, the calibration values, and the dissipation tests that we will see later on, the corrected readings, the intermediate parameters, and the interpreted geotechnical parameters. The chart on the right is a chart which uses two intermediate parameters, in particular ID and ED, available at each test depth, to obtain a more accurate evaluation of the soil behavior. So this is a soil behavior type chart like silty clay or clay silt or silty sand. And the number in the box represents the unit weight of the soil expressed as a ratio of the unit weight over the unit weight of the water. So according to ID and ED, you will have an approximate estimation of the unit weight that will be used to evaluate the effective and total vertical effective stress in the processing. Now let's look at the intermediate parameters we have talked about because they're really relevant for the DMT test. If we perform a DMT test, we will immediately notice that A and B, or P0 and P1, are very close to each other with a ratio of about 1.1 to 1.3. If we are in sand, the ratio P1 over P0 is at least 2.5, and of course the silt falls somewhere in between. Now ID is defined as the difference P1 minus P0 normalized to P0 minus U0, but basically represents the distance between the two measurements. And of course, this leads to a classification of the soil type. But let's look at an example. Here we are in a test site where there is sand at surface and then clay. You see for the sand, P0 is 2.6 and 11.9 with a ratio of about 4 to 5. Whereas below, in the more clay material, you see values of 6, 695, or 6, 7.3, with a ratio of 1.1 to 1.2, for example. Easy. Now, the second and maybe most important DMT intermediate parameter is KD. KD contains information on stress history, which is really important. It is evaluated as P0 and defined as P0, which is the first corrected reading minus the water pressure divided by the effective vertical stress. This is the same exact formula of K0, where P0 minus U0 is the total, the effective horizontal stress. So may we say that we are measuring K0, or is KD different from K0? Well, unfortunately, KD is different from K0 because it is an amplified version of K0 due to the fact that the blade has penetrated. But KD and K0 are very, very well correlated, and also OCR, especially in clay. How do we read the parameter KD if we look at the results? Well, if we are in a clay material, when KD is equal to 2, we are in a normally consolidated material. If KD is greater than 2, the soil is over-consolidated. Let's look at an example. This is a test site where there is a mixture of silt, sand, and clay, and then a lower clay, silty clay layer. And in the first 14 meters, these mixture of silt, sand, and 3 layers of silt, sand, and clay have a value of KD close to 2. So they are basically almost normally consolidated or slightly over-consolidated. Then below, we have a very strong and stiff layer of clay with KD much greater than 2. Now, OCR was estimated using KD with this formula provided by Marchetti in 1980. He went in many experimental test sites that were very well documented around the world, performed a DMT test, knew OCR because the test was well documented, and found that this was the best formula for interpreting the results. It's nice to show that 15 years later, these people, Kamei and Iwasaki, published additional OCR points and found that this formula was very close to the best fit of these additional points, confirming the validity of this formula. There are also publications with theoretical studies using very complex and sophisticated softwares for modeling the soil and showing that this formula is in good agreement with their findings. Similar approach was used, exactly the same approach was used with K0 for obtained from experimental results and research test sites in 1980. And you see how the points lie even more with less scatter on this curve represented by the formula. Again, you may find published theoretical results with the modeling of, for example, the critical state model implemented in CRISP by Professor Yu. Just to show an application of this K0, this is a real case history in 2002 in Sicily, the state of the mafia. There was a landslide very close to a railway, a railway passing underground, and the tests were performed very close to the landslide, number 3, a bit farther away, number 2, and very far away, number 1. And if we plotted the horizontal effective stress obtained from K0, multiplying the vertical effective stress, you see how well it captures the decrease of the effective horizontal stress going from farther away in the undisturbed area from the landslide and closer up to the landslide. And of course, at depth, these lines meet. Now, the third intermediate parameter to introduce is the dilatometer modulus. It is defined as the elastic modulus of the horizontal load test performed by the DMT membrane expansion. So if we accept the hypothesis of semi-elastic infinite medium that you may find in this bibliographic reference and perform some very simple calculations, you obtain this formula, AD equals 34.7 times P1 minus P0. Now, ED is a modulus, but it is not directly usable for many reasons, like the fact that the soil has been penetrated and somewhat disturbed. But the disturbance is very small, and the measurement is a measurement of a modulus to start with. So it is very close to a modulus, but it has to be corrected. How is it corrected to obtain a usable modulus M, the constraint modulus? Well, we have ID, so we know if we are in clays, silts, and sands. And we have the stress history that we saw with KD, if it's a normally consolidated or over-consolidated soil. So when Professor Marchetti went around the world in several research test sites well documented where the constraint modulus was well known, he was able to tune this correction of ED using these other information for obtaining the best formula according to the different soil types with different stress histories and starting from the dilatometer modulus. Now, there are many publications that you may find in literature showing very good agreement between the modulus M obtained from DMT and estimated from odometer data, for example. This is in the continent of US, showing a good agreement between these residual and alluvial also soils. Another example in another continent in Europe, in Norway, this is a very well documented research test site in the northern Europe. And you see the points are the odometer, which maybe exhibit even a larger scatter than the two profiles of the DMT with dashed lines between them. And the third example in the third continent, in Japan, a comparison between the modulus from DMT and obtained from odometer. What about strength? Well, the strength or undrained shear strength SU in clay is obtained using the Schanzepp relation, which tells us that the ratio of SU over the effective vertical stress in over consolidated soil or normally consolidated soil is equal to the same ratio of the normally consolidated soil times OCR to the power of 1, to the power, sorry, of M. Now we have seen that in clays, OCR may be expressed as a function of KD with a formula that has been well validated and published. The exponent m has been estimated at 0.8 by Ladd himself, who proposed or was one of the promoters of this chance-up relation, and the division of SU over effective vertical stress in a normally consolidated soil is usually 0.22 or 0.23. So combining all these expressions, we obtained a closed formula of SU as a function of effective vertical stress, which is known, and KD, which is measured. Now, again, you can find in literature many publications, and I deliberately kept the graphs in their old style. I could have redone them, but I prefer to extract them as they are from the publications, where you see a very good agreement between the DMT profile, the black thick line, and the other tests in these research test sites where the tests were performed very accurately and the test site is very well documented. Another comparison in Canada with the field vein test, which are the points which are in excellent agreement with the DMT profile. Or again, in the same Japan test site I showed you for the modulus, the agreement of the SU is very good with the triaxial test, which perhaps exhibit a little bit of scatter. This is a national research test site of Italy, and this is a publication of the proceedings of this conference in 1991. And you see that the DMT profile is right in the middle of the comparison with the field vein test and laboratory test. And the CPT test was published with different profiles according to the NC value. Now, let me introduce you the C readings, which is the closing pressure after you have expanded the membrane to B and then flushed. So this is a nice slide I like to show, provided by Schmertman in 1998. In this test site, the water level was known, and the points are the C readings. As you see in sands, the C reading lie quite nicely on the hydrostatic line, whereas in clay, the values show very well the excess pore water pressure generated by the penetration of the blade and the impossibility of the water to drain. So basically, when we are in sand, the C reading or corrected C reading P2 is equal approximately to U0, whereas in clay, P2 is greater generally than U0. And this intermediate parameter UD is defined basically as the distance of the point from the water pressure in hydrostatic conditions, for example. And when UD is equal to 0, we are in sands. When UD is greater than 0, we are in clays. Again, let's see an example. Here we are in a test site in a harbor where the material type was between silt and sand. And there was interest to see if it was a drained behavior or undrained. So they performed with in these 5 tests every meter the C reading, and as you see, it lies quite nicely on this hydrostatic line of the well-known water level that was quite shallow at half a meter. So the behavior was fully drained. Now, let's look at the possibility of performing dissipation tests for estimating the coefficient of consolidation, CH, and permeability. Now, the test is a bit different from the procedures we have seen. In this case, we have to advance the blade at depth and start at the origin of the time. Of course, this is done by the software. And then we take only the A readings with time without moving the blade anymore. Basically, we want to study and look at and observe how fast the water will drain due to the penetration of the blade in the soil, which has caused an excess water pressure, and the water will drain slowly, and the speed is what we're looking for. So this is an example of a dissipation test where the flex point was correlated to the coefficient of consolidation with this formula. You can read the details in this publication in 1998 in the Conference of Atlanta. And from that, then we can take we can evaluate the permeability coefficient KH. This test can be done from the cone and also with the blade. The main advantage of the blade is that it involves the the soil in front of the membrane, because the measurement of the membrane involves it's a larger volume of the soil, like a small embankment, and therefore it's perhaps more similar than getting an excess pressure only in a single point that is also highly disturbed by penetration. This is just an historical note of the first validation of the consolidation coefficient obtained from laboratory, measured from the DMT, and from the back analysis in a real project. The DMT and also the seismic are compliant with the ASTM standards, Eurocode, and ISO standards very recently. And another document that can be helpful, perhaps the most comprehensive, is this TC16, which is now a committee renamed to TC102, which reported this document with test procedures and equipment calibrations, which is recommended for those of you who want more details on the test. Then there are several national standards. We are aware of standards in Italy, Sweden, France, China, and perhaps some other country. The SDMT is used in over 80 countries worldwide. You can see that the main distribution is in US or North America, Europe, Eastern Asia, and growing fastly, quite rapidly in South America. Australia and New Zealand are missing a lot of points because this is not updated to the last 3 years, but there have been a lot of increments in that area. In the US, there is an official DMT and SDMT distributor placed in Tampa, Florida. We have started this cooperation since many years, and they manufacture machines that are compliant with both CPT and DMT equipment. So this is for people who are interested in having a representative in US instead of connecting directly to us, which we do serve the most of the world, but in many countries we have very active and cooperative distributors like TMG. Now let's look at some example of tests with also dissipation. This is the new exhibition center in Rome. Actually, it's not new. It was developed a decade ago at least. And of course, it had problems. And that's why we were here just a few months ago doing the tests. You can see the problems in these pictures. I don't have time to go in the interesting reasons of the problems. Basically, there are piles only at the corners. And so there was a settlement in the other part. But anyway, I want to show you the test results. These are the readings, P0 and P1. You can see that the readings are close, the corrected readings. That's why we are in clay. But sometimes they are apart, and we are in sands. And you can see that because the C readings are above the water pressure, but sometimes they are on the water pressure hydrostatic line, showing that we are in sands. But this will be evident also in the ID parameter, the material index, and the unit weight. So these are the field readings and the input of the DMT parameters. These are the intermediate parameters, ID. So we see very clearly that it's mostly a site of clay with some layers of sand or silty sand. The KD tells us that this is mainly a normally consolidated deposit with an upper essiccated crust in the first 5 meters. Actually, the first 2 meters were filled with rocks and stone materials that we had to drill. That's why we're missing the readings. And the dilatometer modulus ED, and the, of course, pore pressure index from the C readings. And as we see, there are some fully drained layers, which are very few, but most of it is clay, expressing clearly the undrained behavior. This is the main diagram of the DMT results. The red is, again, the ID parameter, but you see the colors where the blue, as you see in this legend, is the clay, and some layers of sand are more greenish or yellowish. The constrained modulus and the undrained shear strength evaluated exactly with the formula we saw in the previous slides. The friction angle I didn't have time to show, obtained from the a formula from KD and evaluated for, of course, sands. And again, the KD to give an idea of the stress history parameter, showing again or normally consolidated deposit below 7 meters. So this is the geotechnical parameters, in particular OCR, obtained with the formula of 1980 OCR that I showed you before, yielding OCR equals to 1 with a top crust with very high values, and a K0 that is very nicely equal to 0.5 as in a normal clay, a normally consolidated clay, with, of course, higher values above due to the to this desiccated crust at surface. And this is the horizontal effective stress obtained by multiplying K0 by the effective vertical stress. And then we did a very long dissipation test, in this case with the Medusa DMT, which is able to take a lot of A readings very rapidly with time. And you see the first one was taken at very low timing. And you see this very nice curve with the flex point indicating a consolidation and a permeability coefficient. Now, tests were done, of course, also in USA. This is our dear friend Roger, Professor Schmertman, and David Krabs, some of the experts of the DMT tests. And the instrument was used for the assessment of this road where the shuttle Atlantis was carried before being launched into space. Another example is the testing along a bridge in the east coast of the United States. I'm not allowed to say which bridge, but we did together test with a seafloor system for doing DMT and also seismic testing using a seafloor hammer that you can see here in the left side of this seafloor system. And the results were showing a quite soft clay at the beginning and then a gravel that we had to drill. And then we went below that to obtain values and measurements up to -55 below the water level. And it was nice to compare DMT with pressure meter tests and CPT tests, which allowed to calibrate the constants for the CPT values of strength and modulus. And also the pressure meter gave good agreement with the DMT. And also seismic measurements were performed, showing quite consistent seismograms and also VS measurements in the soft material and also below. Now, in this section of the presentation, I want to focus on the main differences between CPT and DMT to understand what can be the advantages of using both tests, and which, since they are complementary and can be pushed with the same machine. First of all, the flexibility and penetration methods. The CPT is in the CPT test, the measurements are performed at what should be a fixed penetration rate of 2 centimeters per second, necessarily requiring a penetrometer, where the penetration rate may somewhat influence the results. The DMT does not require specific penetration rate because the measurements are performed when the blade is not moving. So the measurements are mostly independent of the penetration rate, and you can use virtually any penetrometer, drill rig, or other system that we have seen. Let me tell you, but we have not time to see it in this presentation, that there's a niche family of silts where the penetration rate may influence the results because there is partial drainage during penetration. So if you go too slow, then the readings will be too low, or too fast, and they can be too high. So with the exception of silts and partially draining silts, the penetration rate does not influence the results of the DMT, at least not very significantly. A second important difference between the DMT and the CPT is the distortions. This is a very famous graph I already showed before in the dissipation slide, showing the amount of distortions during the penetration of a cone-shaped probe, let it be the CPT or the SPT, and a DMT blade. The DMT blade causes less distortions and therefore preserves the original state of the soil. And this means that the soil is more representative of what it is originally before the penetration of the blade, which gives perhaps less uncertainty and less conservative design. A third difference between the CPT or SPT and the DMT is again due to the shape of the probe. When a cylindrical probe penetrates the soil, it creates an arching effect, a well-known effect that acts like a barrier to the horizontal stress that you want to measure. The blade has a ratio between the width and the length of the blade, which is very different from a circular probe, but with very little arching, and the measurement is in the horizontal direction. So this makes it very sensitive to horizontal stress and to stress history in general. Another difference I want to show you in terms of results is this experiment performed by the research group of Lee in Korea. They reconstituted samples of sands with relative density of 40%, 60, and 80%, and differentiated between normally consolidated points and over-consolidated points with blue and white points. As you see, with the CPT, they captured very well the differences of relative density, but not the ability to distinguish between normally consolidated and over-consolidated, which is important. On the same specimens, they did also the DMT test and were able to distinguish different curves for OCR values of 1, 2, 4, and 8, showing that the KD parameter is more sensitive than QC or normalized QC to increasing OCR values. The final comment in the difference between the DMT and the CPT is that the dilatometer, like the pressure meter, performs a direct measurement of a modulus. So this is a qualitative example of 3 different soils which have the same strength but have different stiffnesses. And we all know the difference between and the independence between stiffness and strength, at least partial independence. So if you measure strength, then it's not so easy to correlate back to stiffness because you wouldn't know which, you would need independent information to distinguish between these 3 curves. And this is shown in a different way also in this modulus degradation curve, where Main et al. Placed the various tests and how they the strain rates at which they load the soil when they do the measurements. And as you see, the DMT is in the range for deformation analysis. The geophysical and seismic tests are in the range of very low deformations, and the SPT and CPT are at very high deformations or strains. So when they have to estimate the modulus for the deformation, you may have a factor that may range or significantly. Now, if I had more time, I would have talked about the several applications that can be for which the DMT is commonly employed in in all the continents. Settlements prediction, quality assessment of soil improvement, slip surface detection in OC clays, in situ G-gamma decay curves, estimation of liquefaction resistance, laterally loaded piles, diaphragm walls, input parameters for finite element methods like Plaxis, and shear wave velocity for assessing samples, soil sample quality. We have time just to look at the settlements prediction. So I'm going to show you this application, and eventually, if we have a future presentation, we could look into also the other applications. So when we want to evaluate settlements, we need to have an estimation of the load of the increments of pressure due to the load. So we generally use a Boussinesq for evaluating this additional pressure generated by the load. And we need a modulus for the deformability of the soil that we can obtain from the DMT. So with this very simple monodimensional formula, it is possible to obtain a very rough estimate of the settlement at working loads. That means with a factor of safety, normally between 2, 2.5 to 3 to bearing capacity. Professor Marchetti used to say, I prefer a very simple formula with a good estimated modulus than a very long formula with perhaps including all the phenomena, even of second and third order, but then make a mistake on the modulus of an order of magnitude and make a much larger error in the settlement analysis. These are publications that you can find in literature showing good case histories of case histories of good agreements between measured and DMT predicted settlements, and some of which I will show you here. This is an example of a silo founded on mat with a foundation that was not very well designed, and the prediction of the settlement from DMT was very large, up to 77 centimeters, and this measured settlement about 63, so even well above the factor of safety. But nevertheless, the modulus was very well predicted, and as you see, the blue is the profile of the modulus, and the red points are the modulus back calculated with measurements, I suppose, the thermometers performed at depth in this material that was very soft. So if you're interested, you may read this in the publication of Dusan Berizajevic in 2013. This is a collection of several settlement comparisons in 2018 published by Godleski in Poland. He showed 28 cases of structures in different soil types and showing a very good agreement between the settlement estimated from DMT and the measured settlements after the performance of the foundation, although this was limited to structures with shallow foundations. Another example is this publication in the Conference of Budapest that just occurred a few months ago. 107 projects were reported in this publication showing how the dilatometer test saved the owner significant money over the previously overly conservative design based on less accurate tests, mainly SPT. This is an example of a real test site we did during a workshop similar to this one. Professor Robertson and myself were in the conference room performing a presentation similar to this one, and outside they were doing a CPT and a DMT test, in this case with a drill rig in a very soft material. And in a matter of 3 hours, 4 hours during the presentations, they were able to take out this profile of the SDMT. I omitted the field parameters and just show you directly the main profiles. You see it is mainly a clay with a very low modulus, except in the top part, with even here some stronger crust. Even the resistance or undrained shear strength is shown. The horizontal stress index KD is showing us that below 8 meters, the soil is mainly normally consolidated because KD is equal to 2, whereas above we still have this stronger crust. And of course, the shear wave velocity. Here again, if we look at the OCR parameters and K0, again, we can isolate this top layer of strong crust with high OCR and K0 values, and the lower values with OCR equals to 1 and K0 equals to 0.5, typical of normally consolidated clays. Then, just for the sake of an exercise, we use the settlements program with a rectangular shaped load of 15 meters times 30 meters with a uniformly distributed load of 30 kPa. Then we imported with the uni files the modulus M every 20 centimeters with the measurements that were performed. And immediately we add a rough estimation of the settlements below the center, below the 4 corners, and below the median point of the short and long sides. And it's nice to show and to see in the graph that the modulus, of course, is high in the crust, and then it drops just below the crust, and then it increases triangularly with depth. The boostiness of the vertical load with this, well, we omitted the first 2 meters of excavation. And as you see, the distribution of the load creates a strain that is maximum where the modulus is minimum and the load is still high here at surface. Then as we go deeper, the amount of strain is lower because the load is lower even and the modulus is increasing. And so the estimated settlement, of course, is the number you see here. We didn't do any comparison, of course, with a real case history. So, well, we're very close to the end. This is just to say that one good test is probably worth 1,000 expert opinions and 1,000 tests that provide you lower quality measurements. So thank you for your attention. And I think we have 5 minutes spare compared to the 1 hour. If you have questions, you can do them now or email them to me. You can find lots of documentation with most references I mentioned in this presentation on our website. We are very active in LinkedIn, where we show many of the projects and the case histories, some of which you saw also in this presentation, and an online catalog to see the products or mainly the instrumentation and the parts of that compose the instrumentation. So thank you very much. And Kelly, are you
Yes,
still there?
thanks, Diego. Yes, I'm here. So I have a number of questions. These ones came very early on, and I think you might have touched on some of this stuff, but just practical type questions. So what is the maximum depth to get good data with the SDMT for the seismic? Do you have like a maximum that you've done so far?
For the maximum, when we are in penetrable soils, we went up to 40, 50, I think somewhere between 50 and 55 meters by penetrating with our truck in Venice, in the Venice Lagoon. It's very soft material. But drilling with a borehole, we were able to go up to 140 meters. I would say that the last 10 meters were a bit difficult because the signal was very, very weak. But up to 90, 100, 110, we got acceptable results of shear wave velocity by using also some advanced features like stacking and of course using the backfilled borehole technique that requires some specific instructions that we may provide.
So the next question just asking, why is it called Medusa? Why did you pick that name?
The Medusa was given not from us, but from a colleague who first thought of this equipment. He wanted to use it in only for offshore. He thought of it for offshore, and since it is able to operate in a cableless manner, and you see the membrane like expanding and not, it's like a Medusa means jellyfish in Italian, so it's like a jellyfish breathing and moving on itself. So that's like the story of it, but
Yeah. Nothing to do with like snakes coming out of the head.
No. Medusa in the sense of jellyfish.
Yeah. So somebody asked about the slides, getting a copy of a PDF of the slides. And yes, I asked Diego about that ahead of time. So he's going to PDF those and I will put them on our online learning library. So that link will be sent out to the attendees and also the people that missed it. That's going to be emailed to you an hour after this webinar finishes. And then it said it might take about 24 hours. It's nighttime for Diego, so I'll give him until tomorrow to work on that, and then we'll get it up there for you guys. So next question, asking if DMT is available in the US, and I think you mentioned some of the suppliers. Do you have any other references for that?
No, as shown here, we have an online catalog. Several countries go directly through this e-commerce platform, but especially in the US, many want to have a representative, and we are in very good relations with TMG from Tampa, and they are doing very well, but they're on the East Coast. And yeah, so at the moment, these are the solutions. And if in the future we are talking with other possible representatives for expanding this network of distribution in North America.
Great. So next question is asking about the maximum push force before you would damage the DMT, assuming it's straight, you're not bending the rods, anything like that.
Okay, definitely we have a lot of experience with 20 tons. I heard several clients push without problems up to 25. So that is something that between 20 and 25, I would be quite confident, although my experience is up to 20. We never broke the blade. We broke the rods or adapters because for several reasons. You may have a very soft layer for 20 meters and then very hard, and if you don't know that, your rods will arch and break, but it's not the DMT the weak point, the rods are.
Okay. Next person's asking about a portion of the PY curve. And I think he means what portion of it can we capture with the DMT? And then is it possible to get P ultimate directly from the result?
You mean the PY curves for laterally loaded pile for the pressure meter, because that's something different.
Yeah, that's what I was thinking. And so maybe Ali Reza, if you can just clarify that, we can come back to it. His next question is, how do you compare DMT and pressure meter, like pros and cons of each?
Yes, well, I'm a very good fan of the pressure meter, because like the DMT, it measures directly the modulus, which is very important for assessing deformability, compared to many instruments who measure strength but do not measure directly deformability. I think the DMT and the pressure meter are they are one helps the other, in the sense that when the soil is penetrable, I would do the DMT because you don't have to drill a borehole where you somehow disturb a little bit the soil, because you actually put the horizontal stresses to zero. So that's one advantage of the DMT, because it's definitely the tool which disturbs less in total and also in a borehole. However, the pressure meter has two advantages over the DMT, that when the soil is not penetrable, it can be used because you can drill a hole through rock or through any material that's not penetrable. And also it expands with a higher deformability. I mean, you can expand it to much more than 1.1 millimeter. So this allows you to have a larger curve. So yeah, I think that you can't say that one instrument is the best. You just have to pick the right one according to your site, according to your application, according to what you can do. And definitely the DMT can play a very good role, especially in combination with the CPT, because the machine is the same, so you can do both at a relatively low cost and have a very informative X-ray diagram of your soil.
And then just one comment from another listener here, Bruce Nothdraft, hopefully I'm saying that right. He's just commenting as well that the pressure meter is somewhat difficult because you have to have a very high quality borehole. So difficulties with drilling the borehole, if it's a little too large, if it's not prepared properly, then you're not going to get good results. So there's that added maybe like a little bit more on the con.
Yeah, that's true, because you have to do a calibrated hole for doing a high quality pressure meter test. So there are some very skilled operators that do it, and they do it very well, but perhaps to new users it can be a big problem.
So the next question is comparing now the SDMT with the SCPT. And so what do you think is the additional value over seismic CPT? And is it mainly to capture the horizontal stress components?
For what we have to call it differently. The S of SDMT and seismic CPT is the seismic part, which is totally independent from the DMT and the CPT. So the seismic, as I have shown in this presentation, we put it behind the blade, and that's the SDMT. And we've been asked and now provide, in cooperation with our partners that I showed in this presentation, this SCPT2. So that's for the seismic. It's just a very straightforward way of getting VS measurements, also real time. For what concerns the DMT versus CPT, as I showed in this presentation, I think CPT is very good for profiling and for having a rough estimate of the test site. With the DMT, you can get higher quality parameters concerning deformability, so settlements and modulus. Strength, I would say perhaps a little bit similar to CPT, perhaps a little bit better with the DMT, but they're paragonable. they're comparable, and especially the stress history. If you're looking for stress history, increases of OCR or of K0, then I think there the DMT can be really important for these parameters and for giving you an idea of the history of that deposit.
Yeah, so another question just popped up sort of in regards to that, just asking how just the seismic components of the DMT and CPT compare, and can they be interchanged?
As I said, it's like a piece that you can just get for one or the other tool. You have the CPT, you have the DMT, and then there is a seismic. We sell a seismic that is performed in some places and promoted as a SCPT, but actually it's a SDMT CPT because it has our seismic with the CPT. So I can tell you that from the technological point of view, it is very much appreciated. We have many clients who have both the SDMT from us or the SCPT from our seismic, and also another type of seismic. And they say, as I showed in that LinkedIn slide, if you saw it, that it is straightforward with much less interpretation because we specifically designed it on the in situ experience I personally got in 15 years of site investigations to make it as automatic as possible so that it doesn't need post-processing and it doesn't need an operator, a skilled operator that knows what seismic is in detail.
Yeah, I think the true time seismic is definitely taking off, and your software is really good for evaluating that and looking at the seismic. So whether you use that with a CPT or with the DMT, the seismic is a separate module.
Exactly.
Yeah. Okay, next question. Can the DMT be used successfully in highly organic soils and peat?
Yes, definitely it has been used for this, and there are many publications, even from soils of North Europe and Poland, and some even found some slightly different correlations that work out better than the ones of Marchetti 1980 for very soft peat. So yes, the answer is yes, and in the options of the software you can select these different correlations for these very, very particular soils.
And then in regards to another soil type question, there's one in here asking, what's your experience using DMT for tailings materials?
Yes, tailings is becoming one of the main requests for this equipment, especially in South America and Australia. Also in Canada, we have a client who's using the SCPT, which is actually the S is our seismic, and he's very happy with the instrument and the results. And yes, in tailings dam, it is definitely valuable to increase the knowledge with also CPT measurements and other forms of measurement. We are struggling to work on partially draining materials because both the CPT and the DMT suffer when the material is partially draining, because there it really depends on the speed with which you penetrate. And in this respect, the Medusa DMT is particularly useful, and that's why we're using it a lot in tailings, because it can take A readings or keep the membrane in equilibrium with the horizontal stress even during penetration, like the CPT. I didn't have time to show this, but you can push the Medusa and have the membrane in continuous equilibrium with the horizontal pressure, and it's virtually undrained because as you penetrate, you're measuring the horizontal stress. So this is a new feature that has gotten the attention of many research groups from Austria, where they have these partially draining soils, South America in tailings dams, and Australia. And we have already found there are several publications already talking about results, and I don't have time to explain it in this answer. And definitely, I believe in the next years, many will come more because of the new features that are possible with this automated DMT.
So since we're still talking about soil types, someone also asked about stiff clays containing occasional small gravels. So how does it tend to do with slightly gravelly soils?
If there is a little bit of gravel, it will not be a problem because the gravel will float in a matrix of a finer material, and the measurements will still be valid in terms of interpretation, and the membrane will not break. Keep into account that the membrane was first designed by Professor Marchetti in the thickness of 0.15 millimeters. Then it became 0.20 millimeters. Then he went to a stiffer steel of 0.20, then to 0.25. And now we have when we go in soils that have some gravel, we also provide membranes of 0.30 millimeter thickness, which are very strong and robust and can be used for this type of materials. You don't really lose sensitivity with that because the membrane is not the measuring transducer. It's just a separator between the soil and the gas or the oil if you're doing the Medusa. So if you're accurate with the pressure inflation, and the Medusa does it very well for you because it's automatic, you can be very, very accurate even with a thick membrane. In fact, we're more accurate with the Medusa DMT in extremely soft soils than manually with a thinner membrane. And this allows to survive even with some gravel if it's not dense and if it's somehow floating in a finer matrix.
Okay, so next question is again a comparison of DMT and CPT, but specifically asking about constrained modulus derived from each of those tests and which one would be more accurate or more realistic. What factors would impact the results for each approach?
Well, I was hoping to have responded in the presentation because especially Professor Marchetti, he was very, very keen on this topic for the fact that the DMT, the modulus from the DMT is simply more accurate than from the CPT because it starts from the measurement of a modulus, ED, and it's then corrected using the information of ID, which is the soil type, and the stress history, to which the CPT is insensitive. So basically with the CPT, you have to adopt a factor that can be, of course, varied with other friction sleeve or other information, but still this information is not as reliable as the KD from the DMT, which is like a pivot in the formula for correcting ED and giving reliable modulus, like in the many examples I tried to show you in this presentation, both for modulus and settlements. And also, I didn't have the time to show, but also for laterally loaded piles and other applications where the modulus is really important.
So since you've mentioned it a few times about the time restrictions and whatnot, someone's already asking about, will there be a follow-up presentation to go into all of these other details? So we can work on that. But yeah, I think there's obviously more that Diego can cover on this. And it seems like people are interested in that. Okay, so one last question, because we are running out of time a little bit. So how large of a concern is calibration on the units with the small tolerances of measurements, being in the millimeter range? Are there concerns with contractors keeping the unit calibrated?
Not really. You don't need to calibrate the DMT like the CPT. However, you do have to ensure that when you break a membrane, which happens mainly when you have a gravel soil or when a dense sand consumes the membrane after many tests and eventually it breaks, that you clean very well inside. And we provide you tools like a micrometer to measure the height of the small components inside, which with their sizes already guarantee the accuracy of the expansion of the membrane. So the size of the cylinders inside, which determine when the A and B contacts occur and determine when the pressure readings are taken, are responsible of the accuracy. The user has to just clean very well the system and put them back in place, and we give them tools to make sure the pieces are in place. So it's a little bit different from calibrating a transducer. There is no analog component, no temperature sensitive transducer that can change the values because the pressure is measured separately from the blade.
Okay, so there's just a few more little questions that I will pass along to Diego afterwards, but thank you guys for all hanging in with us. I think Diego and I tied in our estimation of how many people would log in today. I think we were at about 110 to 114 or so. So we split the difference between our guesses. But thank you guys for all joining in. And Diego, thank you so much. It's so great to see you. Ciao.
It was great. Ciao. Thanks. Big hi to everyone. Bye-bye.
Bye.